So in Unit 3, we're going to be focusing on different kinds of energy. The main types we're going to be focusing on today are highlighted in red, the two different forms of mechanical energy, kinetic and potential. Looking at the list of these other ones, they all fall into the category of being different kinds of energy, and we'll deal with some of these later on. Some of the ones we'll focus on as the term and semester progresses is thermal or heat energy. Chemical reactions is one you would have been introduced to during your chemistry class. We will have an entire 2 units during term 2 focused on electrical energy, and even a little bit with electromagnetic and sound later on in term 2. The breakdown of physics is really looking at a lot of things with motion and perhaps more importantly, energy. Our focus today, though, is going to be on the two highlighted initially in red at the bottom, kinetic and potential. The first of the two types of mechanical energy we're going to look at is potential energy, specifically what we call gravitational potential energy. This is energy that is stored up as a result of the position of an object relative to something else. So in the picture, you see a brick that has the potential to fall on the right and one that does not have any potential energy because it is currently on the ground. It does not have the potential to fall at all. Potential energy is dependent on 3 things: the mass of the object, the acceleration due to gravity. If we're here on Earth, we're talking 9.8 meters per second squared, and the height that it is above whatever surface it's being compared to. In the case of the brick, it's how high above the floor it happens to be. But this could be any other surface. It could be how high above a table. It could be the height of a cliff. A number of different possibilities. It has to do with the situation. When you look at the units associated with potential energy, mass is measured in kilograms. Acceleration due to gravity is measured in meters per second squared, and the height of something is measured in meters. This combination of units is something we haven't seen to this point. But to simplify it all down, we use the standard energy unit, and that is called a joule. The symbol for that is a capital letter J. If we look at these two examples, the 2 ski hills, the blue skier simply has more potential energy for one reason: higher height. They both have the exact same weight, which would be where the mass times gravity component comes into play, and then you're looking at the third component, the height. If mass times gravity is the same, height is the only thing that's going to determine the difference between them. Looking at the ball at different positions as it moves down a flight of stairs or as it rolls down a hill, it's all about the height. At position A, we look at it is lower in height compared to what it was at the top of the stairs or top of the hill, where it's 50 joules. Position B, it's going to be lower still, C lower, D lower, all the way down to the bottom where it's going to be 0. So positions E and F, the potential energy is going to be 0 joules for both because there's no height. A, B, C, D will be a little different. They're going to gradually decrease. If we assume that the steps are equally spaced apart, each of those positions we're going to lose 10 joules each position that we drop until we reach the ground where it would indeed be 0 joules. This is an example problem of what a potential energy calculation might look like. The situation here, we're being asked to figure out how tall is the building that Batman would be perched on. We know enough information here to be able to figure this out. We know the mass of Batman and all his gadgets. We know the potential energy that he has. The other piece of information that we do know is, unless we're told otherwise, we assume that he is here on Earth and G is 9.8. So taking our potential energy equation and rearranging to solve for height, it will end up looking like this. The key here, mass and gravity are both on the bottom, so when you punch these into your calculator, you'd want to make sure that you have parentheses around them. Your potential is 282,000 joules divided by, again in parentheses, 95 kilograms times 9.8 meters per second squared. When you calculate that out, you will get 303 meters. You'll oftentimes run into a question that asks you to figure out the change in potential energy. In other words, how much did the potential energy of something change? So how you go about doing this, when we look at our potential energy equation, there's no initial or final. But what you can do is, what will happen with these problems, mass and gravity are typically not going to change. It's the height that is going to cause a change in potential energy. So it will look something like this. Mass times gravity, and then in parentheses, you would determine what the change in height is. A final height minus initial. If it's possible, set your initial height to be 0. If something's being elevated, that works out pretty much every single time. If something's being lowered, then the change is probably going to be a negative value. So a situation like the question, how much is the potential energy increased if an object is lifted twice as far? The object is being lifted twice as far above our object or position that it had been before. So if the height is doubled, the potential energy is also doubled. The other type of mechanical energy is what we call kinetic energy, and you can simplify this down to energy that any object that's in motion would have. It's the energy of motion. The term kinetic essentially translates to motion or movement. So if something's at rest, the kinetic energy is 0. If something is moving, it has kinetic energy. And the equation is pretty simple to recognize that. 1/2 times the mass times the velocity squared. The only part of this equation that is squared is the velocity. But again, if you have a velocity of 0, your kinetic energy will be 0. If you have a velocity that is anything other than 0, then you have a kinetic energy. Taking a look at an example problem of kinetic energy, let's take a look at the flash. So if the flash is capable of running 68,600 meters per second and has a mass of 70 kilograms, we want to know how much kinetic energy does he have. So this one is pretty straightforward in just plugging our values directly in to the equation. 1/2 times 70 kilograms times 68,600 meters per second, that being squared, you end up with a very, very big amount of kinetic energy. 1.647 times 10 to the 11th joules. Now for a little context, when we talk about energy, energy, as we said, comes into play in many different forms. Anything that you consume that's got calories, calorie is another measure of energy, and there is an equivalency between calories and joules. 1 calorie is 4,184 joules, and if we want to throw something in that many people might be familiar with, a Big Mac from McDonald's is on average 560 calories. So we could ask a question like, how many Big Macs does the Flash need to eat in order to achieve this speed? If his kinetic energy at that speed is 1.647 times 10 to the 11th joules, we can do a little dimensional analysis here and know that 1 calorie is 4,184 joules. And then 1 Big Mac is equal to 560 calories, converting joules into number of Big Macs, it would be a mere 70,296.9 Big Macs. Now, a problem like this will get into much deeper, not so much with the Big Macs, but with the calories and joules when we get into thermal energy a little bit later on in this unit. Finding the change in kinetic energy is a little different from potential. When we look at what kinetic energy is equal to, 1/2 mv squared, much like potential, the mass is typically not going to be what changes. It's usually going to be the velocity. So when we deal with a change in velocity, this is going to be a little bit of a different look. 1/2 times m times vf squared minus vi squared. So you take the square of the final velocity, the new velocity, minus the square of the initial velocity. So what this means is the relationship, if the kinetic energy is increased by a certain factor, it's a square relationship. So if the kinetic energy is increasing because something is going twice as fast, the amount that the kinetic energy increases by is going to be 4 times. Because if we look again, velocity squared, let's say the velocity was 2. So that is squared, which would be 4. If the new velocity is twice as fast, 4 squared is 16. 16 is 4 times that of the original relationship for the kinetic energy. The 1/2 m is the constant in this case. So it's a square relationship when the kinetic energy is increased by the velocity. Beginning to bring both of these together, when you deal with an object, very often you're going to deal with more than one type of energy. Something that is moving is always going to have some kinetic energy. It may not be 100% kinetic, but it's going to have some. If something's completely at rest, it will at most have potential energy. Now this one in the middle is also going to have some potential energy simply because it has a height above the ground. This final one down here at the bottom, if we're assuming it's right at the exact moment it's about to hit the ground, the height can be essentially looked at as 0, and it would all have been converted into kinetic energy. But where this kinetic energy comes from is the potential changing into kinetic as it falls. So the final component to what we're talking about today is tying potential energy, kinetic energy, and then another term, work. So if we take this example on the right, a 10-kilogram bucket of water lifted 2 meters off the ground. First, what type of energy does it have? That is potential, because it is at a position where it has the potential to fall. How much energy does it have? Since we know its potential, we use our equation, mgh. So we'd have 10 kilograms times 9.8 times a height of 2 meters to get 196 joules. Now this next question is where this becomes really key and ties in a lot of what we're dealing with in this unit. How did it get that energy? Work. Work had to be done on it. Somebody had to physically move that bucket into the position that it is now currently in. Without doing work, that bucket doesn't gain that potential energy. So when you think about the term work, you got to do something. That's what we're really trying to get at. So the last new concept for today is work. It's the transfer or change of energy. It's measured just like energy in joules. So work can be translated into energy just like the bucket example, and work can be done on something to give it energy in an example like that. How we calculate, however, is a little different. Work is force times distance. Now, we'll deal with this in greater detail tomorrow. But force is measured in newtons, distance is measured in meters, and again, when calculated out, that is equivalent to a joule. So work can be done on an object, or it can be done by an object. So if we look at the concept of forces, let's look at a free body diagram of this bucket situation. So what forces do we have acting on this bucket right now? Since it is at a height and it is supported, there are going to be two forces. Weight of the bucket itself acting downwards, and we are going to have a normal force. The door is supporting it currently. Those two are equal, so the net force right now would be 0. Now the question, what is the minimum force required to lift the bucket? Whatever the weight of the bucket is. Okay, and we just determined that part a little bit earlier, but how we would go about doing that, just like we've been doing, 10 kilograms times 9.8, so it would be 98 newtons. That would be the minimum force just to be able to lift it. How much work is done on the bucket if the door is 2 meters high? So to get the bucket from the floor to the height of that door, work again is force times distance. So we would take 98 newtons times 2 meters, which equals 196 joules. It's the exact same answer we got when calculating out the potential energy that the bucket has. Those should be equivalent to one another. 196 joules of work was done on the bucket to raise it those 2 meters, and as a result, it has 196 joules of potential energy. And this just simply reiterates what we just talked about a second ago. The work done on the bucket is going to be equivalent to the potential energy of the bucket. Okay? And vice versa. The remaining time in class today is going to be for you to work on the Making the Grade lab. A couple of things I'm going to point out in regards to what you'll be doing with this before you go to work. The distances that you measure today all need to be measured to the nearest tenth of a centimeter. So make sure you're using the centimeter side of the meter sticks as you do this. And all of your forces should be measured to the nearest tenth of a newton. You have spring scales that you're going to be using to pull your cart with a 500-gram mass up varying angles of a ramp. Okay, there's going to be a fair amount of rounding today. This is one of the times where we actually do focus on everyone's favorite, significant figures. Your final answers when you're done with all of this today should only have 2 significant figures. Now there is a reason for it, and that's something we'll talk about as a whole class tomorrow when we take a look at all of your data. As you go through this lab, pay attention to the steps in the procedure, the metal crossbars that are at your lab stations. There are attachments to those that allow you to raise and lower those bars. Once you set it at a certain height, my suggestion would be somewhere around 20 centimeters above the lab station. Once you set it, leave that metal crossbar where it is for the duration of the lab. You'll use the large metal clamp to attach the ramp, which is the wood board, to the metal bar. It'll create an angle just like you see on the lab handout. And what you will do to adjust the steepness is to actually, after each set of trials, move the ramp to physically make a steeper slope. You do not have to move the crossbar itself. So, as you go through the calculations, you are going to measure D, which is the physical distance that the cart has moved, starting from the bottom of the ramp until it gets to where the crossbar is. That distance will change from one trial to the next. The applied force is what you'll read on the scale. You'll calculate the work done. Measuring H, the height, that will be the same for every single trial. Once you set the crossbar, it doesn't change. Think about how you would measure the weight using a spring scale. You may have to think back to free body diagrams. Spring scales, if you attach something to them, there is tension. So think about that and figure out how to measure the weight, and then you'll calculate the change in potential energy of the cart. Again, pay attention to your digits as you go through this and answer all of the analysis questions. We will go through the remainder of the lab as a whole group on Thursday. When you get completely done with the lab today, you can begin working on homework number 3-1, which is going to be some practice with potential and kinetic energy calculations.